Dioxide rapidly built up in the atmosphere until it got to a critical point where we had a super meltdown of the ice, and that was the death knell of Snowball Earth.
The carbon dioxide-rich atmosphere trapped the sunlight, increased temperatures, and finally melted the ice. After a 25 million year freeze, Snowball Earth was over. As the ice sheets retreated, something remarkable happened. The greatest leap in the evolution of life the world has ever seen. A leap that would lead directly to us. In the oceans, a few single-celled organisms had survived. After the ice melted away, they began to change dramatically. Roughly 3 million years after Snowball Earth ended, the new warm climate triggered an evolutionary explosion unlike any other. Single-celled bacteria evolved into multi-celled creatures. The first ever complex organisms and the ancestors of all animals, including us. It was the dawn of a new era for life on Earth.
Snowball Earth must have been the closest thing to extinction of early life on Earth that we had. And yet we know creatures survived. And it can't be a coincidence that very soon after the waning stages of this Earth-wide ice age, we get the first large creatures. It really seems as though that series of environmental catastrophes spawned the kind of biology that could give rise to multicellularity.
The key to this evolutionary revolution was oxygen. Before the deep freeze, oxygen levels were only 1%. Too low to support more complex organisms. After the freeze, levels rocketed to 21%. Scientists suggest the boost in oxygen levels was the result of Ice Age chemistry. During Snowball Earth, the sun's ultraviolet rays reacted with water molecules in the ice to produce a chemical called hydrogen peroxide. When the ice eventually melted, the hydrogen peroxide broke down again, releasing huge quantities of oxygen into the air and oceans. The surge in oxygen levels provided the fuel for life to evolve from single to multi-celled organisms. They don't look like much. They're only the size of pinheads. But these tiny creatures are the oldest multicellular fossils on the planet. The first links in the evolutionary chain that eventually led to advanced animals and humans. In the new oxygen-rich atmosphere, these creatures became more and more complex, from just a few cells bound together to creatures large enough for separate groups of cells to assume different body functions. Over millions of years, these specialized groups of cells evolved into the first organs, and that paved the way for ever larger and more complex anatomies. In Australia, Jim Gayling